What's good once again? So in the last video we went about creating a second variable called result, which is a matrix which was statically created, and then we went about creating another matrix, except rather than being statically created, it's now dynamically allocated, and this can be shown here on line 37. And then we created a initmat, which takes a reference to a matrix, more specifically a pointer to a matrix, and a value. And what initmat does is that we take that value and we set every element inside of the matrix of result to that value. And then of course we have printmat, which takes a pointer to a matrix, and it just prints out the context of the matrix. But that's not the end goal of what is to be done in this program. These two functions, as well as the three variables I created, are very important, especially to show an example of dynamic memory allocation for a structure, as well as something more complicated like allocating memory for a double pointer, and then going inside of that double pointer to allocate memory for each pointer inside of the double pointer. But this highlights the power of C and what you can do with it. So what's left for us to do? Well, I want to show an example that I can multiply the matrix. mat1 and mat2, I want to multiply them together and store their result into result, right? The result variable, which is a matrix. This is a different way than what is normally done. There are essentially two ways to have a function. One way of thinking about it is saying result equals mult mat, and then we have mat1, mat2. This is one way of doing things, and this is usually the way that it's done, the way that you as programmers have been doing. But with now using references and using pointers, I can actually do something where I do mult mat, and I can give the address of mat1, I can just give mat2 because mat2 is a pointer to a matrix already, and I can give the address of result. What's special about this is that the third argument, result, we're actually going to be modifying it. So that way here, when I do print mat result, the print mat result before line 54 is going to be different than the one on line 55, because through mult mat we are going to be editing the contents of result there. So with that being said, this actually gives me the format that I'd like to have mult mat. So why don't we go to mymat.h and create our function prototype. So here we are, and now we're going to go here. I'm going to copy this just for now. We're going to change this to mult mat. It's going to be void because, as you saw in the main program, I didn't have a variable get equated to this function, meaning that I'm just going to call it and it's going to do what it's going to do. But here now, so I'm going to take matrix and I'm going to say M1 matrix M2 and then matrix result, or res for short. So this is going to be my declaration for mult mat. So we're essentially going to get 3 pointers to a matrix. So why don't we transfer this and add it to mat.c. So here we are in mat.c. We're going to put this here now. And now we have our function. So one of the benefits of using a structure like this is that the matrix structure that has been created, that I created, has some numbers behind it, namely the row and col attributes or members to the structure that are used for giving us details on the dimensions of the matrix. And when it comes to matrix multiplication, some things have to be considered, namely the dimensions. More specifically, the columns of M1 and the rows of M2. If you don't know, if I have a 2x5 matrix and if I want to multiply it, it has to be 5 by something, right? So if I have a 2x5 matrix that's being multiplied by a 5x3 matrix, this is going to result in a 2x3 matrix. So now we have the dimensions of our 3 matrices that we need. So we need to know that if this is M1, we need to make sure that M1's columns are equal to M2's rows. But not only that, we need to make sure that M1's rows are equal to res's rows, and M2 columns are equal to res's columns. If this is not true and this is not the case, we are going to be in trouble, and more than likely we're going to cause a segmentation fault. So what I'm going to do is that I'm going to add some if statements to kind of safeguard this function from essentially triggering a segmentation fault. Here on line 25, I have an if statement where I check that if M1 row is not equal to res's row, or M2 column is not equal to results column, I want to trigger either or, because both of them must exist. So if either one or the other doesn't, I'm going to run into a problem. I'm going to print, okay, the third argument's dimensions does not match with the first argument's rows and the second argument's columns. I think this is a descriptive way of saying the error. So then to add more details, I print the results row as well as the first argument's row. And then I print the results column that it is not equal to the second argument's column here. And then I return, which will kick me out of the function. Now that this has been accounted for, I now need to check that M1's column is equal to M2's row. And here is the code for that. So here I do the simple comparison. Okay, M1 column is not equal to M2 row. If this is true, I'm going to print, hey, this is a dimension mismatch. The M1 column should be equal to M2 row. And then for more details, I print the two values. And then I do a return, which kicks me out of the function. So no harm, no foul. In both of these if statements, matrix res is not, the data of matrix res is not accessed, or there is no attempt to access the data, so there's no possibility of potentially getting a seg fault. So now what is left is to actually go about the nitty-gritty and do the code for writing the matrix multiplication. So res row is equal to M1 row, and res col is equal to M2 col, right? M1 col is equal to M2 row. So we're representing all three distinct numbers here. So in this case, res row is representing the 2's here, res col is representing the 3's here, and M1 col is representing the two 5's here. So all three variables in the dimensions that we're accessing are accessed here. So what I need to do is I need to go through I and j, which is perfect because it's the res row and the res column. So we'll go through 2, 2, and 3. And then we're going to sum it with the product of various different rows and columns of M2 and M1 based on the dimension, right? So since this is a 2 by 5, we'll be adding and multiplying every row with every column. Does it matter what position these letters are in? Yes, because while I is represented by res row and K is represented by M1 column, the maximum value that I can have will have is 2, which is correct, which is marked by these two. And then the maximum value that K will have is 5. So if we have I and K, we'll have a 2 by 5 matrix. Wait, what's the dimension of M1? It's 2 by 5. So we have some consistency here. So what's the range of K and J? Well, K will go into M1 column, which is 5, which are these two numbers. And then J, well, that's limited by result columns, which is 3 and 3. So we have K and J, which is 5 and 3. What's the dimensions of M2? Oh, hey, it's also 5 by 3. So we maintain the consistency here, right? The idea is that with I, J, and K, we need to make sure of their potential bounds. They go from 1 to a specific value. So since I, the limit is 2, I need to make sure the matrices that I'm accessing have rows of 2. So I should be where the 2's are, which is the row of results and the row of M1. So let's check I on this line. I is on the row of res and in the row of M1, which is consistent here. Good. Okay, what about J? Well, J is limited by the number 3, so it needs to be in the dimension of the results column, as well as M2's column. So let's check res in M2. The column is represented by J and the column is represented by J here, which is consistent because this variable has a max of 3, which matches the dimension that's being accessed here. So what about K? K goes up to 5. So we need to match it with the dimension that goes up to 5, which is going to be M1's column and M2's row. Well, what's that? Where's our K? Well, K is in M1's column and M2's row. So here we have our dimension. Our dimensions are matched together. And here I use I and J to access the data, and I and K and J. I use the square brackets as we would an array to access the data, and you can do this with pointers. So in main, you have seen that I've been doing it this way, which is kind of ugly. It's pretty ugly. And actually, I need to follow what I show, and I need to put, I need to follow what I show and put parentheses here. Don't want to do an accidental double dereference. That's not what I want to do. So we have that here. But what I've done on these two lines is equivalent to what I've done here. I just wanted to show that the two different ways that we can access this dynamically allocated data. And this is multimat. So what's really nice is that because I'm dereferencing here, I'm going to be adding the result that's passed from main. So I don't need to worry about returning anything because I got a pointer to res. And when I edit that, I'm editing result in main indirectly. So with that, why don't we go about compiling and finally testing our code. Oh wow, there's no errors. Oh, that feels so good. So here we go. We have this 2 by 2. We have our zeroed out matrix. We have it 3 by 3, and the result is all 30s, which is correct. You guys are more than welcome to do the math, and if you get a different result, and if I'm wrong, please let me know so I can fix the code. But this concludes our kind of extreme example of using dynamic memory allocation. And this seems kind of overwhelming now, as this is the first time that the concept has been introduced. But as one gets more practice with this kind of tools, and it becomes easier. It becomes easier to use malloc, and it gets easier to use pointers and double pointers and even triple pointers if you ever have the bad luck of encountering those. But anyways, this concludes our rather extreme example in dynamic memory allocation, where we created 3 matrices. We created a function to initialize the matrices and all of its data to a particular value, to print the matrix, and to do a multiplication of the matrix.